So this is the part 5 of the video series on special shear wall design using Intel's program. We have so far discussed the various methods using which we can design the flexural reinforcement of our special shear wall. There are 3 methods basically. One is the CNT method, second one was the uniform reinforcing method, third one was the general power reinforcing. If you did not watch those videos and feel important or feel like watching those videos, you can always check out our webpage and find the video link there. So today's topic is shear design of wall, shear strength design or shear design, whatever you call it. So if we look at how much shear our wall, this compound wall as a whole has attracted, we can find it. Say from earthquake along x direction, we can get the shear. It shows 38. It means actually the axis is 3 for QX, not 2. So the shear is 376. So 376 gives is the shear along x direction, whereas the total base shear under QX is 456 gives. So you can have an idea how much base shear your shear wall has intercepted. 376 divided by 456 gives you 82%. So your shear wall has taken 82% of base shear along x direction, and along y direction for QY it should be shear 2. It is 340 kips. So again 340 divided by 456 is 75%. So almost all or most of the base shear has been taken by this small shear wall. I shouldn't call it small, but as compared to the area, the shear wall is only one, this one. But it has tremendous bending stiffness, tremendous shear stiffness, tremendous moment of inertia, which causes it to attract huge amount of bending moment and shear, etc. to it. So let us do the shear design now. So since we have assigned the general power section or uniform power reinforcing, it has no effect on shear design. You can assign uniform reinforcing or you can assign the general power section to design your wall. It will not affect the shear design. However, you should not assign CNT method for compound shear wall. We have discussed it already. CNT method should not be applied for compound shear wall because all the segments has a common pair P1. You can see the P1. All of this have P1. So it means that CNT will not work here because CNT works, as we had already discussed, for such type of straight walls which do not have other walls connected to it, like this one. This is a C-shaped wall, compound wall. Okay, so for this wall, you have to go and use the general power reinforcing or the uniform reinforcing method. So we are using here the general power reinforcing method, and let us design the wall. Okay, and then power demand cost ratio is 36% demand, 76% demand cost ratio here. So if we click, right click on our wall, then we will have this. We will send it to a PDF. Let's say here, save it here. I have it is saved and opened here. So we have already discussed to you what are the legs. So the information of leg is important now because you're designing segment wise. You're designing leg wise. Okay, leg wise design. So before saving, I should have saved the model in feet unit because the output data is in inch square per inch, which is not what I want. So let's save it again. I have saved the model in FPS unit. Now I have, but I should get US default. I should use US default and then right click on the model. It should be inch square per feet. Yes, it's 11 inch square per feet. Save it again. Save it here. Right. So that's it. This is the amount of reinforcement you need per leg of your shear wall. So we have already given a clarification what these legs mean and what where are those located. in probably part 3 of our video series. However, I will tell most more what how these legs are found. Leg 1 is this one, leg 2 is this, 3 is this, 4 is this. How did we determine that these are the corresponding legs? For that, you need to go to your model and go to the plan view, and then this table, pile leg information, this information is needed. Now, leg 1 is the you need to look at the common coordinate. Leg is the x y coordinates are given here, x1 x2. For leg 1, x1 x2 coordinates are the same. Is the 424 424. X1 coordinate is the same, y1 is different. So let's take our class of 424. It is in feet unit, so let's do the inch unit. Here where it is 424, along the length of the member is 424. Here you can see at this point is 424. Okay, whatever. This point is 424. This point is also 424. So it means that this wall is the leg 1. The leg 2 has common coordinate along y is a 378. So this is what it is 23. This is 378. So this is the wall. Is a leg 2. Okay, this is a leg 2. And the leg 3 has x1, x2 data common is 502. So 502, you see 502, this is the 502. So this point is 502. The upper point is also 502. So this is the wall. Is a leg 3. So it's gone. It's gone. It is gone. The only one left is that one. Is a leg 4. It has common data along y 23. Since y data is same, it means that it is a wall along x direction, right? If your x data is fixed, same, then it means that your wall is actually along y direction. Okay. So leg 4 has 293. So along what? Along y direction. So it's horizontal wall. So see here, it is 293. 293, 296. So this one is a leg 4. So now look at the shear design now. The combination is reported here for which the shear reinforcement is designed. The applied shear is 231 kips for this leg, 279 kip for that leg. So you may ask that we saw that the shear that this whole wall intercepted from the building or two was only about 85% or 80%, which was 376 kips. So how come this single leg takes 231 kips? So it is possible for this leg to take 231 kips from 378 kips, because if it is 231 kips, how much do you have? 31 minus 378 is 147. It means this wall is taking 147 for under this single combination. So it depends on the combination, because a combination has a lot of things associated with it. It has accidental torsion included in it. Also, the orthogonal effect of the um, another orthogonal earthquake loading is also a concern here. That orthogonal earthquake may also produce some in-plane shear on that wall due to geometry and interconnection between the overall structure. So 231 kips, the structural wall needs a river area of 0.42 square inches per feet. This leg is the leg 2. This one, this has a shear demand of 280 kips and requires 95.9695 inches square per feet. You may say this data and this data are pretty close. There are only 40 kips difference. Then why the reinforcement has been doubled? So it is because this wall length is very long. So the concrete contribution in the shear capacity is high for this wall, but concrete contribution for this wall is lower than this. So for example, in 231, this wall gave about, say, for example, 60% capacity from concrete. The remaining 40% was taken by this uh, reinforcement. For this 279, probably only 40% capacity was contributed by the concrete, but the remaining 60% or 80%, whatever percentage was needed to be taken by the reinforcement. So this reinforcement is high. Again, leg 3 and leg 4, we know this. Leg 3 needs this reinforcement and has this applied shear force. And of course, you see the 5BC here. From 231, about 153 kips was taken by concrete. Remaining portion, about 80 kips, was taken by the steel. Here, in 279, only 60 kips was taken by concrete. The remaining 220 kips was taken by the steel. So that's why the steel volume or area is very high. Then leg 3 is this one, and leg 3 has 163 kips shear force applied in it, and the required reinforcement is 0.62 inches per person. However, it may come to your mind that leg 3 has a length of about, say, here, leg 3 has a length of 85 inches. Then why the concrete shear capacity is very less, such as 6.5 kips only, whereas the leg 1 had a concrete capacity of 153 kips with a pile length or leg length of 103 inches. It is because the formulas involved in shear capacity determination. If I take you to the CSI guideline, not the CSI guideline, is the SWDACH 1808, which I had shown you how to get it. You can get it from documentation and then shear wall design, and then you can choose a code from here. ACH 1808 is my applicable code in my case. So if I open it, I had already opened it, and if you go to section 221, then you will find how to determine the shear capacity of a wall. So in this formula, you see that VC is a function of the, here is a concrete F times C, and the shear wall length is the LP. And 3.3 lambda square root of F times C, TP is the thickness of the wall, 0.8 LP. It actually means in case of, beam design, we use D here, right? D. Instead of D, in case of shear wall, they are using D equals 0.8 LP. And there is another part associated in this calculation or the formula, that is a function of the axial load. So if you have tension is positive in model, right? However, there may be two interpretations of this. Say if I show you the force, say for example, Qy and tension, you will get a compression force here. But if the force is applied from the other direction, then there will be tension in the wall. So again, there is another issue, which is when you get a bending moment like this one. Say for example, the bending moment is in kip inches, so 86,000 kip inches. So when this bending moment is applied to the wall, then some part of the wall legs will be in tension and some part will be in compression. For example, for this case, if we consider that the bending moment is with respect to the x-axis, negative x-axis, okay. So let me show you that in paint. Let's say the bending moment is with respect to this axis, negative x. So this looks like this. This is the bending moment. Probably I can put an arrow, or this is the bending moment. Okay. So in this case, you're having tension here. Let me put this color for tension. There will be some tension here and here, but compression, I'm using red color for compression. Compression in this wall, right? So these wall segments will be in tension, and this wall will be in compression for this particular bending moment. So you get that the shear design of a shear wall per leg, you have to go per leg, okay, for shear design of your shear wall in a compound shear wall. But if your shear wall is a single leg shear wall, then you don't have to worry. The program will automatically report a single leg, and the shear capacity and shear checks will be given accordingly. So in our case, you see that here 626 skips. So this is positive here, but it's actually compression. Okay, when something is reported in your calculation and it has positive sign, it means it is compression. And if it has negative sign, then it's actually tension. But again, when you check in your model the force, and if you find it tension, then it shows positive. The force is positive, recorded positive here. So for example, if I look at this, then it's compression and the sign is negative here. So how can you be sure of what I said just now? So for that, for being clear about it, you can assign different fire section to your wall segments. Okay, so I have assigned different fire segments. As you see here, it's 12, it's 13, it's 14, and it's 1 here. And then if you check the fire demand capacity ratio, I have assigned the uniform reinforcing here. So just go there and assign uniform reinforcing with this or any reinforcement data. We are just taking the shear capacity now. So the assigned axial or the main reinforcement will not govern here. So now go to the fire demand capacity ratio and then right click on this wall. Then you will see that this leg is designed. Now, since this fire has only one leg under it, so this leg is reported as leg 1. Leg 1 has shear capacity failure at the bottom. It says that river required is overstressed. So the associated combination, which is responsible for this failure, is this RCC72 QX minus QY minus, and the associated axial load is 317 kips. So let's check it out how much axial load we get for RCC72 QX minus QY minus, and remember this number 317. Okay. So RC7 QX minus QI minus has been chosen from here under combination, and fire is selected there and then apply. You see there is 317. You can see let me move it, create it. Now you can see that there is an axial load of 317 kips. So I said that if you directly check on this screen and look at the axial force diagram, then tension will be reported as positive. You will see from here. Okay, tension is reported as positive 317 kips. But when you go to the output of the calculation, then tension is reported as negative here. Okay, so there's the silly difference that I wanted to point it out to you, because it may cause confusion in your calculation if you go to do the calculation manually. That you may not get the actual result if you make a mistake in PU sign. Okay, so PU is actually positive in this formula. If you have tension in your shear wall leg, then you have to put the PU as positive. Okay. Then if you put PU as positive, then what will happen? VC will be reduced. So this is a simple case actually. If you have a wall or a member like this, and you are pulling it from two directions. Okay, from two directions you're pulling it, and you are checking your shear capacity at this section. So your shear capacity will be less because the grains are pulled apart. So interlocking capacity is reduced, right? Interlocking of the grains in your concrete is reduced due to the tensile force applied here. So what happens is if your tension applied tensile force is very large, then VC might turn out to be 0. In some cases, your VC might be 0 if PU is very large. And if you get, let's say, for example, negative value from here, PU is so large that you get, say, a negative 20, negative 50, whatever, or you get directly 0. In that case, ETAPS will report here a 5VC equals 0 kips. For leg 4, it reports a 5VC value of 0 kips, and for leg 3, it reports a 5VC value of 6.5 kips. So this is the reason the concrete contribution in shear capacity is so low for leg 3, whereas for leg 1, the shear capacity is 153 kips. Okay, so I think you have got an idea why this is 0. And again, there are other formula which are applicable to the shear capacity. Okay, in case if it is a special shear wall. Okay, if your shear wall is a seismic pier or seismic shear wall, then additional shear capacity formulas are applied in in addition to this calculation, which are actually for non-seismic shear walls. The seismic shear wall shear capacity formulae are also applied. Okay, so whichever is less, the shear capacity is reported accordingly. Okay, now say that where were we? We were here. No, we were here. Now you see that for your leg 2, you have gotten OS here. Is the shear capacity over stress. So since they have got 5 is equal 0, all the shear capacity needs to be supplied by the reinforcement. And for reinforcement, there are again some criteria regarding reinforcement. When you resist your shear force by reinforcement, you cannot actually go beyond 6 square root over FMCBD. You can find it in chapter 11 of ACI 318. Say, for example, in case of beam shear strength design, the total shear strength is 8 root over FMC, in which concrete contributes up to 2 root over FMC and steel is allowed to contribute up to 6 square root over FMC. However, you cannot exceed the 6 square root over FMC by steel alone. So when this happens, then steel rebar over stress is reported here. So what can you do now? So we have already said that there are a few options which you can utilize now. For example, if we go back to our model and then go to the revised preferences, then we have some safety factors here or reduction factors here. Not safety factor, is the strength reduction factors. So phi shear is 0.75 and it is non-seismic, and for shear seismic it is 0.6. But the court said that you can go up to 0.75 if there are some conditions, of course, if you provide a large amount of shear reinforcement, more than that required by your analysis. Say, then now let us move to the fundamental or the basic nominal shear capacity of a shear wall concept, which I had shown you in probably the first video, in which we had done some literature review. So here, here it is the NHRP seismic design of cascade-based concrete special structure walls. So I am reporting you the references from here. You will find it in BNBC and ACI course as well. So what does it say? For wall shear, including shear friction, ACI 318 allows 5 equals 0.75. Okay, so it's reported in BNBC as well. 5 equals 0.75. However, 5 equals 0.6 when nominal shear strength Vn is less than the shear corresponding to development of the wall. Wall nominal flexural strength Mn. Okay, so let us see now how much bending capacity our wall has. So I'm assigning it, say, assign pier section. Okay, pier section probably. What we will do? We'll assign the general pier reinforcing, and then probably this one was our refined pier section, and check it. Then what we can do is we can go to the define general pier section again, and then pier 1, 2, and then modify show pier section. Get into the section designer, and then we can check from here the interaction surface. From here, interaction surface, you see that what is the applied axial force and what is the bending capacity from here. Before that, let us see how much axial force we have in our wall at this moment for various combinations. Say, for example, I'm checking under envelope combination for reducing time spent. So the pier, I should assign a single pier here, shell pier level, maybe it's open already, pier 1. So let's check the axial force again. It is about 1600 kips. So now again, so and what is the max? If there's a detention, no, the minimum is 466, the maximum is 1600. 466 to 1600. Okay, so it's actually more detailed than what I'm doing at this moment. I'm just trying to shorten it. So let's go to the um, what is it called, interaction surface diagram. Exclude the phi, okay, because phi is not involved in the mm. Okay, so what are you trying to find? Nominal shear strength, okay, with respect to the wall nominal flexural strength. So we are trying to find the wall nominal flexural strength first. So the applied um, axial load is about 1600 kips, and for 1600 kips you get a wall bending capacity of 15,754 kip feet. I have already said that for our in case of our model, the applied axial load is about 1600 kips, and for negative 2652, the bending capacity is decreased. So the bending capacity is increased with increase in the axial compression. For when the axial load increases further and reaches 4,400, the bending capacity increases by about 5,000 kip feet between those two values. So let's say in our case, the applied load is 16,000 kip feet. Sorry, 1600 kip feet, which is close to the 1789. So let's take this value. It is 15,754 kip feet bending moment. So let's write it here. The nominal bending moment that can be, obtained from our shear wall due to the provided reinforcement is 15 or what? Let's go back and check it out. 15,754. Let's say it is 1600, 16,000. So it is 16,000 kip feet. Now we have to find the nominal shear with respect to this. You can do this in several ways. There are some, what is it called? Thumb rule that the height that you will choose to develop the equilibrium is about 70% of the total wall height. Let us have a look at it. This is the total wall height. And if we look at, say, angular velocity 20 or whatever, and then look at the bending moment, what do we get? This is the diagram we get. So it is a maximum, and they're showing the applied bending moment is 7,600. Now we have to find the 0 point from here. At what point the 0 occurs? So we will actually find it under RCC 5, say for example, I don't know, under which combination the momentary 3 will occur. What is it? It's only, yeah, it's 7,400. So okay, fine. So this is here it is positive 479, 479, 264, 22, and then 0. So what is the height where this becomes 0? It's about 37 feet. You can look at here. Is about 37 feet. Okay, 37 feet. And above it, there is not much bending moment, but the sign is different here. So if now if we go to there and try to draw this, let's say this is our shear wall. Sorry. And this is the 37 feet level. The wall height is probably 78 feet. So at about 50% height, you're getting the zero bending moment, and you are having a bending moment like this. So this bending moment, in our case, it is 16,000, the nominal bending moment. Let me go back to my model and check it out once more whether I checked it correctly. Is it 16,000 or what? Was it in kip feet unit or kip inch unit? Kip feet. Oh, of course it is in kip feet. Okay, fine. So let's go there. So now it is 0 here, and the minimum is 0 here. The height is 37 feet from here, from the bottom is 37 feet. So if you take a moment with respect to this point, then what will we have? So let's say this moment is clockwise or what? Anything you can choose, no problem. Let's say this moment is clockwise. the applied shear will be this direction. So if you take a bending moment with respect to this point, then what will we have? We will have 16,000 feet equals the Vn width into 37. So we will have Vn equals 16,000 divided by 37. How much is it? It's about 432 pips total shear. So our shear wall has to have a bending, not bending, the shear capacity, nominal shear capacity of 432 pips minimum. Okay. So this is the Vn. So we had shown you previously, if you remember in other videos, that in our case, the applied shear is about 370 kips, but when the reinforcement yields and forms a plastic hinge, then the applied shear will be 432 kips. You have to multiply it probably by 1.25 as well to convert it to the expected nominal flexural uh, strength. Actually, this will have to be multiplied by 1.25, the flexural capacity. So the Vn will be 432 into 1.25. The code didn't actually mention the expected nominal moment strength. They said the nominal moment strength. In that case, 1.25 is not required. But for safety, you can use the 1.25 because we are using a flexural reinforcement of 60 ksi, but in reality, the flexural strength, yield strength of the rebar will be high. It may be 70 ksi or 68 ksi, etc. So that's why 1.25 factor is used along with the rebar flexural strength and rebar yield strength. So that in that case, the Vn will be 1.25 times higher. So what you need to do is, so how much is it? If you take the ratio, say that you had about 370 kips applied shear, now it's 432 divided by 370. So you have about 20% excess shear here. So what you can do is you can provide shear reinforcement in excess of what you get from your design. Say if you have a shear demand of, say for example, here you have here 0.8 square inches per feet. Say you provide there 0.8 into 1.2, then it will be 0.96. So it means that you are providing shear reinforcement considering the development of plastic hinge and the corresponding shear force applied at the development of the plastic hinge, which is the Vn we have just calculated, which is about 430 pips probably, something like that, 432 pips, yes. So in that case, what you can do is you can increase your phi factor from here. You can make it 0.75, okay, and then redesign your shear. After your redesign, let us now check whether the OS, which was reported here somewhere, is available or gone. It is gone now. You can see from here that the OS, which we had seen before, is no longer available. For example, we had an OS for leg number 2. Leg 2 was probably which one? This one is the leg 2. It had an OS in shear reinforcement. Now it's not there because of increasing of phi factor. So now, what is the required reinforcement maximum? So we are going to provide maximum reinforcement in all of the legs. It is 1.11 square inches. So you can directly go to any program, for example, Word. So required shear reinforcement, because how much is it? 1.11. Okay. 1.12 square inch per feet. So there are two legs. There are going to be two legs, right? In your shear reinforcement, like this. One leg is this one leg is that one. So we will calculate how much required for one leg. So per leg requirement. This leg, I mean by rebar leg, okay? Per leg requirement was 1.12 divided by 2 gives you 0.56 square inch per feet. So let us say we will use a spacing of say 3.5 inches. So now let us find the area of single bar required. Okay. So how to single bar area or shear bar rebar area required is it's 0.56 into 3.5. 3.5 is this spacing and divided by 12. Divided by 12 is because of this feet. Okay. So as we are calculating the required divide in square inches per feet, so we have to divide this by 12. So how much do we get? We get 0.163. So it's very close to the river area of a 12 mm diameter. Use 12 mm river, which has an area of 0.175 square inches. However, in our practice, we do not use 12 river up to the first story. We have a practice of using 16 river at a spacing of 4 inches center to center. So if you provide, say, that reinforcement, so if you provide 16 reinforcement at the rate of say 4 inches, two legs, there are two legs, then how much do we have? We have 1.87 square inches per feet. Okay. So in place of 1.11 square inches, we are providing 1.87 square inches per strip or per feet height. So I think the shear calculation of a shear wall is pretty clear to you now. It's actually a little bit more complex than the flexural design because it encompasses many issues, and there are a number of formulas which are of concern here, and your privacy is becoming zero at a number of locations due to the presence of tension in your pile leg or shear wall leg. So I hope the video was helpful to you. Thank you for being with us. Okay, another thing I forgot to mention is whatever reinforcement grade you use in your shear wall design, shear design of your shear wall, you cannot exceed 60,000 in your shear strength design. Okay, say for example, you have used 500 MPa rebar or 72.5 KSI rebar for your shear reinforcement, but you can use it. There is no issue in using it, but you cannot consider your material property more than 60,000 in calculation. Okay. So, for example, if you go here, ETABS already knows that if you go here and rebar material, if you choose here 60 KSI, then okay, rebar material 60 KSI is for the flexural reinforcement and for shear. If you choose from here 72 KSI or 100 KSI, it doesn't matter. ETABS will actually lower it to 60 KSI for its calculation. However, when you do manual calculations, you have to keep it in mind because ETABS does it automatically because it has it inbuilt, but in your manual calculation, your Excel will have it inbuilt. In that case, you have to always remember that in case of beam or column or shear wall, etc., you cannot go beyond 60 KSI in case of shear strength capacity calculation of your member. Okay.